Okay, thank you, Luke. I appreciate being able to talk about something I'm really passionate about, which is VFDs. I've been involved in my whole career and power quality, which was one of our main strengths. Um, our company, Energy Management Corporation, is started originally as a multi-generational company in the motor repair business, and now is in the fourth generation, which is strongly in the electronic motor control, generators, motors, drives, and power quality. So about a year or two ago, I did a presentation for the IEEE chapter in Southern California, Orange County, who wanted to have more discussion about the projects or the technologies of variable frequency drives considerations. This is kind of what some of the things we talked about then. On this presentation today, we have a very broad audience, so I'm going to take just a couple of those items. Everyone wants to know what caused the problem. Was it the VFD or the motor? And what effects do VFDs have in the electrical environment? So that'll be the main topic with system compatibility in the electrical environment. But I'd also like to start off with discussing a little bit about the history of VFDs. Like Luke said, I was a co-founder of Energy Management Corporation back in 1979, which was really the advent when VFDs started becoming very prolific in the industry. Before that, primarily, the only way to do speed control was through mechanical devices. We would change shifts on a motor with a pump or a fan, and that would, of course, give you one level of speed control every time you change that shift. Then a company called, well, I think it was US Motors, had the VeriDrive, which was actually a pulley combination that automatically changed the shifts into variable speed, but it was all mechanical and very uh, problematic from a maintenance standpoint. Eddy current clutches. I remember Eaton Dynamatic in the early days being very popular in that area. And of course, in large machines, in AC machines, for long periods of time, almost since the GE and Westinghouse original large machines, they were used of resistors or capacitors to give you some level of speed control. But the main thing that was used in I'd say the 40s or 50s were the DC motor drives. And early on, you probably remember the MG sets. We actually had a motor powering a generator to develop the variable DC voltage to have those original DC drives. And this all kind of correlates with the advent of the devices that were necessary for VFDs to become popular and economical and reliable. That's one of the things our company prides itself. Whenever we work on a project, we want to always consider improving the safety, the reliability, and the energy efficiency. So back in the 20s and 30s, GE uh, actually developed, patented a device called the Thyvatron, which was a type of gas tube diode, which was allowing power to either go through in starting some of those early DC drives and some of the AC drives. That developed into the thyristor, which is called simply an SCR nowadays, silicon controlled rectifier. That was the real workhorse in the 40s, 50s, 60s, and 70s for DC drives and different types of ways of taking power through silicon to have some kind of variability. The drives that were built in those days, um, in probably the 70s, there were a proliferation of, well, actually, back even in 1960, a company in Finland called Stromberg came up with the first variable frequency drive using silicon devices. And they sold the first project, this would be a low voltage drive, to I think the Helsinki Railway, which they actually got that up and operating 10 years later. So in the early 70s, that was the drive that Stromberg came up with. And in the meantime, Other companies like GE and Emerson and all these companies were working on drive technologies, starting with the silicon control rectifier, SCR, and had a first generation of drives that were either based on a voltage source or a current source kind of technology, which was very problematic in having the motor compatibility, where you had to have almost the drive matched to the motor with many of those early technologies. As things developed, when I came into the picture, Luke mentioned Westinghouse. We represented a company called Vectrol that was out of Oldsmar, Florida, back in the early 80s. And they developed a device, or actually commercialized a device, that was developed at NASA called the NOLA controller. And it was basically monitoring the back EMF of a motor and then phasing the voltage back using SCRs to reduce the voltage and reduce the magnetic flux to save some energy. And that was, like I said, originally a patent of NOLA. Well, that company, Vectrol, after a few short years, was acquired by Westinghouse. And as Luke said, I was privileged to be the commissioning agent for serial number 3 of the Westinghouse Accutrol 300 drive, which was based on the next generation of an SCR. They called it a GTO, a gate turnoff thyristor, which is the same as a thyristor, same as an SCR, except it had a gate where you had these big drivers, so you had to use current to actually stop the flow of current. And that allowed you to get some control at low frequencies, talking about maybe a kilohertz of switching frequency back then. As things progressed with the Westinghouses and the Emersons, a company called Parametrics in the very early days, and Ramsey's and Lovejoy, if anyone knows those names, they're as old as I am. Those are all gone by the wayside, either acquired by other companies, but those were the ones that started the first PWM drives, where we used pulse width modulation to synthesize a waveform to the motor that the motor is compatible with and likes. And so after the SCRs, the gate turnoff thyristors, the bipolar transistor is what really drove those devices. And the Japanese were very, very good at that. The Toshibas, Mitsubishis, Yaskawas, they really kicked off the advent of reliable variable frequency drives using PWM control. And those early ones were bipolar transistors that soon developed or soon transitioned into IGBTs, which the main difference would be that it was easier to turn that transistor on and off, and it could operate at higher frequencies. So now you could switch at 10 kilohertz and almost have that whining noise become silent in HVAC applications. And as we keep going on down the road, right now, everyone, I would suggest, would be working on or has a product with silicon control, or with silicon carbide MOSFETs, or GaN, a gallium arsenide, and the new technologies we call wide bandgap. The main difference there is now we can switch into hundreds of kilohertz, and they can be very, very efficient. And part of what drove that so much would be the electrical vehicles, which use a form of variable frequency drive. It just starts with DC rather than AC. And those are primarily based on silicon controlled, silicon carbide MOSFETs. And I think we'll see a lot more from that. As you look at that advent of the history from the vacuum tube all the way to silicon carbide devices, different challenges occur along the way. And that's where my career has kind of been developed in saying, okay, if we do one thing, what unintended consequence does that have? To get into exactly how these things work, and this might just be a little bit of a repeat for some of you, but a typical 6-pulse PWM drive, the kind that we have several thousand of in stock right now, from 1 horsepower to 800 horsepower in 230 and 460 volt, have a topology just like you see here, where there's a diode front-end bridge, a DC section with capacitor filtering, and an inverter section where you convert the DC to AC using that PWM. Well, the way this works is you've got, in this case, a 3-phase waveform here. When your first wave is increasing in voltage, where it goes through the diode and it overcomes the level of bus voltage, then it commutates on, and that capacitor now swallows that current that is what I kind of refer to as the gulping effect, which causes this voltage sine wave, which is very clean and pure, to have a current sine wave, which is not sinusoidal and is gulping like you see in this bottom slide. And so that's really the impetus of some of the challenges associated with VFDs on the line side of the VFD is that you're charging capacitors that are being discharged by the inverter section, and as fast as they're being discharged, that diode front end is recharging them in that gulping fashion. Now on the back end, on the inverter end, and of course variable frequency drives start off as adjustable speed drives, adjustable frequency drives, inverters. Inverters comes from the fact that you're really taking the DC and inverting it back to AC and just using transistors. And that's done with a PWM waveform, which turns that voltage on and off in different widths, which synthesizes the waveform. So kind of like you see in this right bottom graph, if you take a number of very small pulses and longer pulses, that would look to the motor similar to what a waveform would look like. And so, while not perfect, the motor can tolerate it. While not perfect on the input, it generally in all of the 70s and 80s grew and grew and grew in popularity. And the primary reason for this is because of something we call the affinity laws, which is a huge motivator in applications for flow loads that can reduce energy consumption. So the affinity laws would apply to like centrifugal fans and centrifugal pumps, where your flow and your pressure and your speed all have different relationships. So if I take this fan curve and look right here at 100% flow and 100% pressure, and this could be as well, could be a pump, and there's where my curve is going to start. That's going to be 100% speed also. Now, if I reduce that, if I come down that curve and reduce the speed to 80% speed, I still have 80% flow because flow is proportional to speed. My pressure, on the other hand, is down to around 62 or 63%. I don't need as much pressure to operate at that point. But the real magic is speed reduces as a cube, theoretically. So I'm looking at 80% load or 80% speed, reducing the horsepower required by almost 50%. And of course, any kind of process that doesn't need to always have full speed is going to be greatly enhanced with something that can reduce the speed of that motor and thereby get that natural law of following the affinity laws of reducing the horsepower requirements tremendously. So as that technology started becoming a little bit more mature, the applications for variable frequency drives just skyrocketed. Pumps and fans being probably the predominant ones because every building or every industrial process with a centrifugal pump or fan are going to have huge savings. And this is now getting into the 80s where we're having energy crises and a real desire to be motivated to reduce energy. Also conveyors and compressors. And one time I was going to write a book called 101 VFD Applications. Well, it's easy to find out, well over 100. I've got a list of well over 100 right now, but I've got a few I'm just going to bring up. And during the question period, if there are particular questions you have in the applications, because I'm not going to go through them all right now as to what you would do differently in one versus another. But for example, in a fan or blower, you have facilities all over the country that have old technology that might be using bypass valves on a pump or a throttling valve or a throttling damper. And if you approach matching the airflow to the occupancy needs or the environmental needs by just reducing the speed of the motor, you get that large savings, which in most of those kind of applications easily is in the 20 to 30% range. And of course, when there's light occupied conditions, but still need to have airflow, even much greater than that, to the point where it's probably common practice now for almost every design engineer, mechanical and electrical, to implement variable frequency drives in new buildings that would have fans or pumps. Cooling towers is another interesting one. You know that that's probably, if you go and look at a manufacturer's catalog for two-speed motors, you see less and less of those now, because you can have 100% or 50%, perhaps with a variable torque two-speed motor, but with a variable frequency drive, if you need to operate at 70%, you can operate exactly at 70%. And you can adjust that based on the temperature of the water that that cooling tower is cooling. So we saw most cooling towers being replaced long ago with variable frequency drives. Water and wastewater pumps, again, whether it's a municipality or uh, a local HOA development, most all of those are using variable frequency drives to maintain pressure um, in the system, as well as the right amount of flow on need. Same thing with the lift stations, and of course, other advantages of the variable frequency drive are similar to your reduced voltage starters or soft starts. You can ramp those in a way that avoids water hammer, and can decelerate the same way to have many advantages. Of course, in the manufacturing area, a lot of that really is important in reducing the wear and tear on the drivetrains, or in the case of a bottling factory, actually having a ramp that's optimized to not drop the bottles off the conveyor, but optimize the speed to get it up to speed. So these are additional types of applications. Um, go on down to mining. Same thing in crushers, for example. Lots of wear and tear on the drivetrains. We've done those and almost doubled the life of the wearable components. Same thing with machine tools. In drilling here shown as having a very optimal uh, speed for drilling through certain kinds of surfaces, or in the case of machine tools with aluminum, or what the depth or the size of that is, you can optimize those processes by easily changing the speed of the lathe or the mill. Elevators are a no-brainer. Almost all of those were DC before. Now they're almost all AC drives. Booster pump stations in a multi-story building usually stage on levels of motors, and at least one of those stages is always going to be a variable frequency drive. Now, usually they'll put, even if there's 3 stages of pumping, they'll probably put all of them on just because of the benefits of the reliability. And agricultural irrigation systems have become very popular just because it's one of the best ways to really control the usage of water on crops. When we talk about some of these applications, I'm reminded when I was in New Zealand, I saw almost all of the irrigation there was done by submersible pumps, where here in the West, at least in the US, it seems like everything is a vertical hollow shaft turbine pump. When we get into submersible pump applications, it's, for me, very, very important that we look at the length of wire between the drive and that motor, and especially when it's not in a media of air as an insulator, but in water. We almost always apply sine wave filters because the effect on windings is even more detrimental in that application where it's in a submersible well. Dynamometers, of course, I've mentioned even vehicles. Every electric vehicle is based on variable frequency or inverter technologies. So as we look at some of the applications, if there are specific questions, like I mentioned in the submersible pumps, that's just one to, I know in my own HOA, we just installed an output sine wave filter after the last failure they had, just because we know that that's a vulnerability of the motor in that particular environment. So I'm going to move on to the environment, which I talk about as the electrical environment. Like I said, we could talk about applications in how do you size a variable torque load or a constant torque load or a constant horsepower load. which get into more unique applications like winding machines or um, machines that need to develop a high amount of torque. But I hope to keep this somewhat general, and if there are any specific questions, we can address those here in the end. I hope to leave 10 or 15 minutes to be able to do that. So when I think of the electrical environment, harmonic distortion is probably not a term unfamiliar to most of you. That's become a big issue on the electrical grid. And conducted and radiated noise, EMI, RFI, are often referred to as EMC, electromagnetic compatibility in Europe. There are many standards associated with those. And then, so that's from the drive feeder side, or the power supply to the drive. We're going to look at those issues. And within the next 15 or 20 minutes, talk about that and specific electric motor compatibility issues like DVDT precautions on windings and also bearing currents. One of our great engineers a number of years ago brought up this slide next, talking about the environment that I just kind of love. You know, this is not, we don't have new problems. We do have new problems all the time, but we got started with old problems. He called it the Great Horse Manure Crisis of 1894, when in New York, now the the carriages and cabs and everything that was now modernized to be drawn by horses, and this ended up with a population of 100,000 horses in New York City to pull all of these cabs and wagons and carts and devices, generating 2.5 million pounds of horse manure per day. I find that kind of amazing that when we talk about the environment, that over 100 years ago, it wasn't any different. In London, you see in the next slide, just piles and piles of manure where they had over 11,000 horse-drawn cabs and carts and over 50,000 horses. So that's a classic example of an environmental problem that now we as engineers, we really get to work, and we work hard, and we're going to solve that. And so here's our solution. We developed the horseless carriage, and we now push the manure crisis to a air pollution crisis. And so everything kind of has its way of implementing or causing unintended consequences to develop. And the advent of the variable frequency drive, and in general using silicon devices and having power electronics going now rather than through the way they were originally developed by Tesla and Edison and Westinghouse and all those great engineers that used sinusoidal and DC, in the case of Edison, transformers. There's now a very different consequence associated with having non-sinusoidal waveforms going through transformers and breakers and transmission lines and protective devices. And so I want to bring up a typical one line of an electrical system nowadays, modern electrical system, and point out where many of these challenges may now occur because of this little variable frequency drive right here. And I need to remember, the reason we're putting up with all of this is because of the phenomenal benefits of the variable frequency drive, like the energy efficiency, the improvement on the drivetrain wear and tear, and even the protective technologies is so much greater than ever before in being able to shut down a faulted device. But as we go upstream from that VFD, the first thing that we could affect would be the cable that's going to be affected by that harmonic generation that the diode section or the converter section of the VFD is consists of. Certainly the circuit breakers and earlier circuit breakers you might have experienced in a plant, tripping a breaker unintentionally. That could even happen from just upgrading to an energy efficient motor, because the energy efficient motors have less losses and higher peak starting currents. But with variable frequency drives, now you're introducing some fifth harmonic and seventh harmonic and other harmonics that are going to add up into that thermomagnetic breaker, but they're really not doing any of the work. They're just being developing additional heating in that breaker, which needs to be taken into consideration. And that could, even in the transfer switch, even though it shows a problem, the sensing of the voltages, which are usually on the line side, that's transmitted now from the drive all the way back to the utility. And so everything here is going to see those harmonics. Dry type transformers are going to be the most challenged. I remember doing a big retrofit project with a power plant where we converted over a dozen large cooling tower motors, and they had a dry type transformer feeding that particular cooling tower, which we had to develop some special harmonic mitigating reactors for each of the drives that reduce the distortion and the stresses on that transformer, which would have overheated based on the numbers that we were reading of the voltage harmonic rise. But the utility transformers, while a little bit more tolerant when they're especially oil filled, that's one of the first concerns is there going to be an overload in the transformer? And the utility's ultimate concern is when it gets back into the grid, are other customers going to be affected by that? And I'll get into what they've done about that and where their concerns are. Following a standby generator, the same kinds of problems are going to be potential in the circuit back to that generator, where now you've got a voltage regulator looking for, following the voltage, which could be distorted now and could go into an instability problem if there's too much harmonic distortion. And we have lots of opportunities to solve problems associated with a VFD being implemented on a standby generator that needs to now consider how do we go about that and make sure that's not going to be a liability of reliability failure. From the output of the VFD, we'll also, like I said, talk about briefly the effect that PWM waveform, that pulse width modulated waveform, has on the cable. And nowadays there's even an inverter duty cable that some manufacturers say you got to have it. You've got to solve this problem. Cables are usually pretty tolerant, but there are some situations where that really is a factor that needs to be considered, and especially in the motors. I said my father and my grandfather, and I grew up in a generation of motor rebuilders and individuals that were always sensitive to what caused the motor failure. In our case, in the 70s, I was very interested in how do we rewind a motor to be able to take the different kinds of waveforms and some of the challenges that we see in motor failures and make that better. And so we created an inverter duty rewind way back in the 80s, just because once you recognize the problem, there's always a solution. So to talk a little bit more about this harmonic on the line side, the cause of that, or what that's all about. When you think about our 60 hertz grid here in the US, 50 hertz in Europe, the fundamental frequency is 60 hertz. If you now have 180 hertz on that waveform, which would be a single phase third harmonic, or a fifth harmonic, which would be at 300 hertz, now you're starting to add other waveforms that are riding on top of that 60 hertz. And that's exactly what's starting to happen when you start putting electricity through silicon. And in the case of, I've removed most of the slides to not make this too technical of a presentation, but a simple depiction of this is your orange line is now the 300 hertz level, where the gray is my 60 hertz waveform. The resulting waveform is that blue line, which is an extreme level of harmonics in this particular case. If I were to mitigate that a little bit, it looked like two double humps, like you saw in one of those earlier pictures. And so there are some predominant frequencies that are developed based on the kind of solid state topology that your drive or welders or computers or power supplies or just about anything is going to experience. So as we simplify these harmonics, which you have a range of these, we usually look at them up to the 50th harmonic, but really there's not too much that causes us problems through about half of that. And to get a term that you might have heard of, total harmonic distortion, It's simply the summation of the square of each of those harmonic currents and the square root of that over the fundamental 60 hertz. That comes up with a percentage that is harmonic distortion. It might have 20% harmonic distortion, current or amperage harmonic distortion, or 100%, or whatever that number is. That means something as we add up all of those harmonics and now quantify what that is. If we take a waveform today in any one of your facilities, we would then take a meter or monitor that does power quality analysis. We'd see a certain amount of, let's say that we've got 30% harmonic distortion, current harmonic distortion. We would then do a fast Fourier transform and get it back into all those levels of frequencies to be able to know how to solve that. But at the end of the day, with too much harmonic distortion, problems are going to be caused both in the plant and at the utility level. And these are a few of those that we recognize easily. In single phase loads, you probably remember when cubicles in office buildings were burning up. Those were because of so many computers being added and having a high level of third harmonic neutral to ground, which they actually changed electrical code to say you have to oversize those. So that was probably everyone is aware of that has been in electrical field of codes. Nuisance tripping with blowing of fuses or overloads. System resonance. If you've got power factor correction capacitors in a system and it's been working great for 20 years, and now you add a variable frequency drive, a frequency, that fifth harmonic, 300 hertz, or seventh harmonic, based on the system impedance, can easily resonate with capacitors way upstream, and even in some cases with utility capacitors. So system resonance, well, right over here, overheating, easy destruction of capacitors, blowing of fuses, all those things have been very prevalent as we've looked at more and more ways to mitigate harmonics and where the susceptibility is going to be. Power factor correction is certainly one of those. D-rating of transformers, you've probably heard of K-rated transformers, simply a transformer that's rated to handle so much nonlinear load or distortion. Erratic operation of standby generators, like I mentioned, a generator can only handle so much distortion before it's going to not be able to regulate properly. And then ultimately, utility fines and charges. I've heard of a couple where utilities have said, if you don't resolve this, we're going to turn the power off. You're going to disconnect power because we believe that it has a negative effect on our customers upstream, which is almost like the historical water utility or in our own homes. We think of power, and we've got the voltage, which creates the pressure. It's similar, analogous to pressure. We've got the flow, which is analogous to the amps. And we've got valves, which would be just like these devices, cut-off devices. But the backflow preventer is not really available in the electrical system. It really consists of how do we mitigate harmonics either at the source, or now how do we cancel those out or trap them or do something about them so they don't go upstream into the utility grid, which could affect other customers. So that analogy of a backflow preventer, I think, is a great one. And so almost all utilities I know have embraced IEEE 519. I'm sure many of you have heard of that standard. In 1981, one of my friends, Ray Stratford, was a co-chairman of that, and they developed that as a recommended practice in the very early days. That's gone through about 4 or 5 revisions now. This, I think, is I don't know if it's the 2014 or the 2020. But this is primarily where it is today. And what IEEE 519 says is, depending on how large of a customer you are or how you compare to the source capability of the utility, which they look at that as ISC, or the short circuit that is at the common coupling where the utility comes and connects to you, compared to the IL, the load, how large you are. So if you have a utility that has 100,000 KA short circuit ability, and you are 1,000 amps of that 100,000 short circuit, you're going to come into the chart here at 100, which should be somewhere in this area here, and they're going to say, all right, we're going to allow you to have 12% total demand distortion. But if you're a great big user and you've got 5,000 amps of power you're going to take from my grid, where I'm limited to 100,000 kA short circuit, I'm going to require you to be down at a 5% total demand distortion. And if you're a smaller user, 20% is a reasonable number. And so this is IEEE 519, which has some other caveats. They limit in between, you know, the so much between the 11th and the 3rd harmonic and all the way up to the 50th harmonic, which are usually not so problematic. But that's how IEEE 519 actually evolved nowadays to no longer recommended practice, but a standard which all engineers would use in prudent engineering of a facility. And so therefore, either they're going to have provisions to say, okay, we need to reduce the harmonic distortion from these devices by this much, or we need to have a device that doesn't create it. Even fluorescent lights, when we changed from fluorescent lights through magnetic ballast, which were primarily a sine wave linear load, to the LED modules, which now have drivers in them, which are a little solid state device going through silicon. Even the good ones nowadays, bad ones would be in the 30, 40, 50, 70% distortion, current distortion range. The standard now is somewhere around 20%, where if you're a manufacturer, Sylvania or Philips or whoever, they're going to have one of the specification points be that we're going to be below 20%. And that's pretty common for them. It's easy in a little fluorescent driver to have some active harmonic cancellation to get that down. So it doesn't cost them a whole bunch of money. But when you get into a 1,000 horsepower variable frequency drive, dealing with thousands of amps, that's a much more difficult issue. So if there are any questions about IEEE 519, I don't want to spend too much time on that, but that is an important thing. That is the recommended practice that tells us what we're trying to do. So I go to the tale of two universities. Back in these early days when IEEE 519 came out, one engineer that we were selling to in his university said, I don't want another drive from you guys until you solve the harmonic issue. Another university said, well, we're not seeing any problems, so we're going to just keep, buying them and not spend the money in that. Well, it's kind of one of those things where you pay me now, you pay me later. Ultimately, when you add so much distortion to the grid or to your building, there's going to be a problem, and then you have to go back and dredge the lake. Nowadays, in most specifications for variable frequency drives, there's some kind of level of harmonic mitigation already required. Actually, back in the early 80s, because of that engineer at that university, we said, okay, we're going to work hard, we're going to find a way to do this, and we got one of the first patents for harmonic mitigation associated with variable frequency drives, which we didn't think would even last more than a few years because it'd all be solid state in the future. But still, we find today this is one of the most economical ways, using passive harmonic filters to mitigate the different types of harmonic distortion. This just shows quickly, a VFD could have 65% fifth harmonic and 41% seventh, but even your computers are going to be way up in there unless they have now new harmonic corrected power supplies, like some of these newer LED lights that are a little bit more expensive, but that's solving the problem in the equipment side of things, office PCs and so forth. Here's an example of a typical PWM 6-pulse variable frequency drive with no impedance on the line side. And that would typically come up to 70 to 120%. And again, that's because of that gulping effect that's coming back through here, and there being no impedance like a line reactor, which is the waveform of this is even discontinuous. It goes all the way back down to 0. That's that typical double hump. We don't like to see that very often. Small micro drives, maybe not a problem, but the larger the drive or the load becomes, the more problematic. It's very, very simple, and we have thousands of line reactors in stock, and they're typically used in variable frequency drives. You can apply them at any impedance level. You can apply them in creating filters, lots of things that can be done. And lots of drives have either a DC reactor or an AC reactor as standard. The only problem with that, and it's a good idea, but when you put it inside the drive, there's a pressure to optimize whether the size of the drive or the amount of the impedance is used. So we tend to like to put our reactors in the system outside the drive and have the most compact and most elegant drive technology, but some have it inside, and that helps you can get down to 30 to 40% very easily from that 100% number just by adding a line reactor. And so uh, one of our engineers that was the director of engineering at Geneva said, I will put a 5% line reactor in front of every variable frequency drive that I ever buy. And that was his first practice. When you do that, you change that big double hump to a smaller hump. Now, it doesn't look elegant, but it looks more like a sine wave than not in this particular case. And quick graph showing there's a diminishing returns. You don't want to go up to a 12% impedance. 3% is a pretty good number. 5%, that's where you typically see reactors available in the commercial markets. Passive harmonic filters, this goes back to that like that patent that we developed where now you have a tuned circuit here with a capacitor and a reactor that is trapping the fifth harmonic or the frequencies that we tune to into this trap, so it's not, with a little bit of impedance here, it's not going out onto the line. That's the standard art nowadays. Our patent, we licensed it to a number of companies that used it for until the patents ran out 20 years later, and now everyone has a technology with slight variances on that. In our drive systems, we integrate that harmonic filter along with DC inductors and other devices to create a drive system with harmonic mitigation that now at that source, you can only be putting back onto the line the amount of harmonics that was designed for, which could be as low as 5% or more economically 15 or 20%. Those filters operate quite well, even with voltage variations. So with a let's say 8%, 5 to 8% range from 40% to 100%, had very good performance with that, even with voltage imbalance, which causes some technologies of harmonic mitigation to be challenged in not maintaining the original input. Here's a simple 12 pulse pseudo system where you could take just two transformers and phase shift one of them. If those two drives and motors are equally loaded, you're going to reduce the harmonics substantially right off the bat, maybe 12% harmonics with that technology. And there are also other ways of having a phase shifting transformer. Well, when you get an 18 pulse, that might be more clearly defined. The challenge with that is when you have voltage imbalance, it does, and with load deduction or reduction, you do have some loss of mitigation of harmonics. This is very, very popular technology. See a little bit less of it nowadays, but in almost all municipalities with larger drives, 18 pulse is exactly the same as 12 pulse. It's just phase shifting with 3 bridge rectifiers, and a little bit more complex on the front end. Usually requires, well, it does require an 18 pulse phase shifting transformer. Here, I've got a picture of one of those. Here's what the topology looks like. 4 to 15%. Oftentimes we see 5% being achieved quite easily when the voltage imbalance is contained. This is what that looks like. Here's that big phase shifting transformer, one that we built. And we endorse all methods of harmonic mitigation. There are some better than others in certain applications, and that might be something to ask about in the question and answer session. So this is what that looks like, and these are the other diode rectifiers added to an existing just regular 6-pulse drive that has one set of diode rectifiers. And again, pretty good harmonics, down close to that 5% range, unless you have big voltage imbalance. And if you're 50% load or better, still pretty good reduction. Active front ends has been traditionally very expensive technology because you're basically taking the one variable frequency drive and almost adding another, and usually the cost has been almost the same as 3 regular 6-pulse VFDs. But what you're doing now is you're taking the same inverter section that converts the DC back to AC, but your converter section is now an active device. So rather than being diodes and rectifiers, these are active devices that you can now fire on in any particular pattern for what your objective is, which could be optimizing harmonics. It could be regenerating back onto the line. It could be improving power factor. You can do a lot of things with control. You've obviously complicated things quite a bit, but there are now becoming more and more active front end variable frequency drives. Still fairly expensive, but there's certainly a place for them. The reason that they get expensive is because you almost always have to have an LCL circuit. So you still get back to having a pretty significant set of reactors and capacitors to get rid of now the high order switching frequencies. You've still got that gulping effect, and you've still got power going through silicon, which now even gets a little bit more difficult to handle because the higher orders of those switching frequencies cause more problems in the EMI RFI area. Here's an example of this. That's how big that filter is for the LCL filter. So not a small device by any means. And the last technology I think I'm going to show here is one that we've really seen a lot of recently, the active harmonic filters, where you take a device that now is in parallel with the rest of the bus, could have multiple drives, and I'm going to just speed along here a little bit faster. It's almost the same technology as noise canceling headphones, where you just generate a waveform that is the opposite waveform to cancel this out. Might be this, it ends up with this. So the same thing you hear audibly with head canceling or noise canceling headphones. You can do the same thing with active harmonic filters, and there's some very significant advantages of these devices. They are, again, much more expensive than passive harmonic filters, kind of more in the order of the active front end, but there are some applications where that can be almost equal to the passive filters in multiple drive applications in particular. Here's an installation of some of these active harmonic filters, and very, very flexible, great way to be able to drain the lake afterwards by canceling out the harmonics at your main system, and also being able to control power factor. Here's a system, I think this one is in Pearl Harbor, where we have an active harmonic cancellation of that variable frequency drive. I'm going to skip past this. If there are any questions about the cost effectiveness of the various kinds of technologies, this top one just as an example of passive harmonic filter here being the bottom, the most cost effective, and the most expensive being 18 pulse as you go into small sizes, and everything else in between. Medium voltage, we won't get into, but there's a whole other set of technologies and multi-levels for that. Generators, I'll just mention because when you have any variable frequency drive on a generator, you need to be concerned about the alternator. And there are methods of doing calculations to make sure that you don't have too much harmonics, but typically if you get below 10% THD, you're getting in the range where the alternator won't be negatively affected. So now I'd like to spend the last maybe a couple of minutes anyway on the output of the drive. DVDT, I'm thinking that most of you have seen a motor failure, heard of a motor failure. It really is that the turning on and off of these silicon devices have a very fast rate of rise. And if that waveform gets to the end back to an impedance here, it can be reflected back and even double. And so where you have a 480 volt VFD being at maybe 750 or 650 DC volts, that's what the motor is going to see, is a switching on and off of 650 volts. But it can be as high as 2000 volts in the worst case of this phenomena of reflected wave. And so most motor repair facilities, like all of those of us in NOR, have now methodologies of improving the integrity of that installation. And motors also have now followed new motors. The new MG, not new now, they're fairly old, but part 31 of MG1 now would say to call yourself an inverter duty motor or capable of having inverter waveform not damage the motor, they're going to be 3.1. They're going to be able to have an insulation to handle 3.1 times the rated voltage, a rise time less than 0.1 microseconds, and being partial discharge free. And here's some examples of, here's the waveform. Here's what that looks like when you start seeing reflected wave. You can measure that. Here's what, if you put in simple reactors or a little bit more sophisticated DVDT filters. And I talked earlier about the pump, submersible pumps. At some point, you just have to have a sine wave. And so here's a sine wave filter. Example of DVDT filters and reactors. There are different levels of quality with reactors and where they can operate, and flux density and polygap or distributed air gap is one of the things that we talk about. If there's an interest in going to that detail, we can talk about that. Last thing I want to just briefly mention is the bearing fluting, or the problem of the bearings becoming damaged because of partial discharge, which when you have that frequency that is adding up as a capacitive coupling at your motor, at some point when that flashes over, there's a partial discharge. And bearing currents have become very well known in the industry, especially in the motor repair industry. And there's many ways to be able to, a number of ways to be able to solve that. One of the easy ones is putting on insulation, ceramic bearings and shaft grounding, fiber optic or fiber types of grounding rings, which has worked very well for us. You can also have magnetic solutions where you reduce the common mode. And so I wanted to have us a little bit more time. Sorry that it took a little bit longer, but maybe we can get a few questions here, Tyler.
Yeah, yeah, absolutely. Can you hear me, Steve?
Yes.
Okay. We got two here that we might be able to actually combine into one answer. The first question was, where does the utility measure harmonics? And kind of accompanying that, should they be mitigated at the drive or somewhere else?
Okay, that is a great question, and it really is two different questions. Let me handle the first one first. IEEE 519 defines the PCC, point of common coupling. Now, most of what I have seen that to really be would be the line side, the utility side of the supply transformer, which would be the high voltage. Technically, if you had a utility trying to cut you off, you'd probably go back and look at that and get to that technical definition, because there's going to be a lot of attenuation through that transformer. But most utilities are measuring on the secondary side of the transformer. In other words, where that power comes into your first switch gear, which would be particularly maybe the 480 volt side. So if you get into a legal battle, I try to push it back onto the primary side. But on the secondary side, that's going to now be the culmination of all of those harmonics in your facility that are going to end up with a certain amount of current harmonics. Now, granted, you're never going to be harmonic free. The utility is going to have 1 or 2% voltage harmonics probably already there, but they don't want to get any worse than that. So they're going to measure, and we've seen them go out and measure on the secondary side of their transformer or at your switchgear or at your main. And then they would say, okay, we want that to be between 5 and 20%, whatever the short circuit to IL ratio becomes. And now you've got a decision. If you're now having to clean it up later, and you've got some variable frequency drives back in your system, and if some large ones, you might be able to go back there and say, hey, I'd like to put a harmonic filter on that, or this drive's getting really old. I'd like to replace that with one that now has harmonic mitigation. The drives we're going to see in the future, while they're still expensive now, as we get into silicon carbide devices, we're going to see high switching frequencies and even more types of harmonics, super harmonics, that are going to have to be dealt with. There are no standards for yet. And so we're going to have to deal with those at one point or another. And there are some drive manufacturers that are already offering these, and they have paid a lot of attention to the filter networks at the drive. And so you could replace any old variable frequency drive with a new one with a certain standard of harmonic mitigation. But if that's not convenient, you could go back to your main or any point in the system and now do that noise canceling. and say, okay, I'm not at a point that's makes sense for me to go back and change all my drives. I've only got a few, but I would like to get the harmonics down just a little bit. You could add harmonic correction right there at the main or even at a particular MCC bus. When we do drive fan walls for some of the universities, it's not practical to have each of the little 7.5 horsepower drives, there may be 30 in a cabinet, to have each of those have harmonic mitigation. So we would associate an active harmonic filter right at that MCC that takes care of that load, and then all the way from that MCC upstream, there's no harmonic effect. So it really comes back to the application. We'd love to talk about that because there's no one perfect solution for all situations, but there are solutions for all situations.
Great. I think you touched on two different questions also that came in. Real quick, while I ask those, feel free, everyone who's in attendance, you can still send in questions through the chat or the question and answer function. But one question, you might have answered this, but I'll ask it anyway in case there's other things you want to mention. Is it worth replacing older VFDs even if they're still functioning? Are there any benefits to just modernizing those?
That's another great question, which the answer is it depends, right? One of the things we replace old technology and drives almost every day. At the same time, we have drives that have been operating for over 30 years now, and that technology is quite old. What you find, the older the drive, the slower the switching frequencies, and some of these EMI, RFI, or the problems that we're going to be seeing with the higher switching devices, higher frequency switching devices, are not existent. And the harmonics are still going to be there to the majority of extent, because you're not going to get rid of harmonics, but you're going to get rid of a lot of the other noise, EMI, RFI issues. We typically find that when we do an analysis for a customer, we did one for an oil company for all of their compressor stations, and they wanted us to analyze the benefits of replacing the drives based on several things. One would be you can get higher efficiency with the newer devices, just a little bit. You can't, like in an energy efficient motor, you get fractions of a percent. It's the same way with VFDs. You don't get big percentages like you do with the like the affinity law, changing the speed of the drive or the motor. But the factors would be, is it still reliable? Is that drive a reliable vintage? Can I still get parts for it? And that's probably what drives a lot of the decisions is, hey, I just can't get a part for that Allen Bradley drive or that Square D drive or whatever. Most manufacturers only offer them for 10 years. They kind of force you into an obsolescence if you don't have the spares to go out that far. But from a technology standpoint, if you want to now start solving some of the problems that are getting bigger because you've got, like in a steel mill, you have arc furnaces and all kinds of harmonic generating devices, welders, lighting, UPS systems, everything you think of that goes through silicon is going to generate harmonics. And at some point, you may start wanting to replace those devices with cleaner devices from an environment standpoint, from a harmonic standpoint. And so we do know most of the replacements we do are replacing older drives that didn't have that with drives that do have that. But the reliability factor often is the key area. If it's not broke, don't fix it unless you have another reason.
Great. Thank you. One other thing you touched on fan walls for a second, and one question was, can you compare HVAC or other systems using one large VFD and motor compared to multiple smaller ones?
Interesting question. We've done both, very typically. The answer somewhat comes back to redundancy a little bit. If that one drive goes out, you've got that whole fan wall system out, and you are going to save a little bit of money by having one large drive and one harmonic mitigating filter. You could actually use a passive device let's say you have 25 horsepower drives and you get one big 100 horsepower with a 100 horsepower passive filter, which would be the most economical way to go about that. For the last couple of years, I've seen much more orientation in going to having each motor on an individual variable frequency drive. Drives are not coming down in price like they did during the 90s. We were seeing variable frequency drive pricing reducing, almost every year. Now they're more stable. They're not really reducing in price, but they're pretty economical. And so last number of packages we put together include a drive and a line reactor, maybe 20 in one package. The customer now has the ability to control the speed individually if there was some reason to do that. But more so, each motor is protected individually, and there's plenty of redundancy to take the top of the fan wall out or maintenance issues or whatever that is. And to be able to have the harmonic mitigation, the most effective way, again, comes back to injecting the harmonics to mitigate those 20 drives at the MCC or at that cabinet. That's my opinion, and it's probably in any particular situation there may be other nuances, but we'd be glad to talk about that if anyone has additional discussion on that.
Great. Another question, you might have mentioned this just in passing, but how common are DC to AC conversions, and what do you need to consider when you're doing that?
DC to AC conversion, the power electronics industry is just chock full of that now because of everything that's electrifying is now coming off of batteries. Airplanes, ships, boats, cars, is going to be a DC to AC, and that's just the inverter section. And those have very, very sophisticated technologies in both the windings for those kind of motors and in the power electronics for those kinds of motors. And they still have to solve shaft currents or bearing current issues in those. But you're starting off with anything that uses alternative energy, solar farms or whatever, can benefit by going directly from DC to AC. Even in some systems, like in a fiber system, textile industry, you would maybe take a DC bus and now only have 100 little drives that are DC to AC for each of the spindles. So that becomes very common. As far as in a typical AC motor, you're always going to have to convert your main source of AC to DC first. But there are lots of applications jumping up in the industry of driving the prices and the availability of power electronics because of strictly the DC to AC inverters. I don't know if that answers the question or not, but that's probably more of those than anything now.
Okay, great. One other one that we've got here, and then I saw a raised hand, so we might have one come in after this. But is there a benefit to having harmonic mitigation in separate devices and not integral to the VFD, or is it better to have it internal to the VFD?
Oh, that's again a question that says it depends, because you can buy an active harmonic filter, active front end, which almost all of those would be. It's just like in the new LED tubes, they have drivers that have a small semiconductor that can now actively switch that small amount of current and do anything they want with it. That's how they get down to that 20% really easy. You can do the same thing in VFDs by having an active converter section, and you can solve that and other problems actively. You are a much more complicated device, so we don't have any of those on the shelf. They would be more specific applications because they're going to be much more expensive. If there was for example, maybe certainly in the aerospace industry, if you were dealing with 400 hertz or something special like that, you would have all of that included within a device and maintain the EMI RFI inside that same device because it's so critical in like a military or ship application. And that would already be existing in the industry, as is simple active front end devices. The benefit, so there are benefits of that, and the biggest benefit, if you need regeneration, if you need to have your power flowing back out to the grid like you do in your solar inverters, or we did an application up in Alaska where they were unloading wood chips into ships, and so it was a downhill conveyor, and we had to have we had to have two things. We had to have low harmonics and we had to have regeneration. Well, regeneration, you do that with an active front end, and so you're already willing to pay for that. So once you're willing to pay for, if you've got an application that needs regeneration, it's a no-brainer to use an active front end and all built in. On the other hand, when you think about an active harmonic filter, which is technology that's been really taking off, the Eaton, Siemens, Schneider, Square D, all have these, and I offer them even in MCCs as part of your MCC switchgear, are now saying, okay, how much harmonics do I need to correct? So in the case of let's say a good application for an AHF would be a pump station that has three 100 horsepower VFDs. You've got a lead, a lag, and a standby. And I could put three passive harmonic filters on to be able to operate any of the modes, or I could put one active harmonic filter. And the benefit of an active harmonic filter to begin with is if I've got reactors in there, I'm not dealing with 100% of the load. My harmonics only be 30%. So I need to size that active harmonic filter to 30% to inject that much onto the line to cancel out the 30% harmonics coming from that first load. Now, if I've got now two of them, then I'm going to have rather than 200%, I need 60% current. So I inject 60% current at those two being at full load. The standby is just going to rotate back and forth, and so I don't have to worry about that. So there's a case where an active harmonic filter doing it outside the drive has a really big benefit because you don't pay any more than for the most inexpensive technology like a passive filter. It's that inexpensive when you only need one of those and you only need to process 1/3 of the load. And those devices are now coming out with silicon carbide at very high efficiency rates, which really, again, drive a real case for using active harmonic filters in more and more installations. Where it doesn't make sense in my mind right now is you have one big 500 horsepower variable frequency drive. You've got to, and now I need to provide, let's say, about 1/3 of that. That's still a relatively expensive addition onto that drive. Of course, an active front end would be very expensive too, but you'd have to have, some of those are in modules of like 100 amps or 150 amps. And as you start stacking more of those modules to go for one single drive, it may not be as cost effective, where it's almost a no-brainer when you've got multiple drives.
Great. All right, that's all the questions we had come in. So I just want to thank everyone for attending, and Steve, thanks for your time and your expertise. If you do have more questions, or if anything else comes up, you can find some of the resources from our company at goemc.com, or the resources from the entire Nowhere Network at nowherenetwork.com. Thanks, and we'll see you in the next webinar.